Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. And we're in chapter 1 part of this playlist called Probability. And we're in the last video of this chapter, which we're going to cover Bayes' theorem. Now, the topic of this video is a theorem formulated by the Reverend Thomas Bayes in 1761. And it states this: Bayes' theorem is let A1, A2 through AN be mutually exclusive events that partition S. That means the union of these disjoint sets is equal to S, and it called partitions it. Let event B be such that the probability of course is greater than 0. Then for any of the events AJ, the probability of AJ given the event B is equal to this probability. And notice that the conditional probabilities are reversed. So this is the probability of B given AJ times probability AJ divided by the sum of these probabilities. Probability of B given AI times the probability of AI. Now, a quick proof of this is you first have to note that B can be partitioned into these disjoint sets. So A1 intersect B, union A2 intersect B, all the way to AN intersect B. The union of these disjoint sets makes up B, right? So the probability of B, the probability of these unions of disjoint sets is going to be the sum of these disjoint sets. So it's the union of the disjoint sets. So the probability AJ given B, standard definition of conditional probability is the probability of the intersection, AJ intersect B, divided by B. But B can be written as the sum of these unions, right? So these, and the multiplication for conditional probability tells us this is the probability B given AJ times probability AJ. But we can use the multiplication rule for conditional probability on this, and we obtain the denominator in the theorem. And so the result follows. So now let's use it. This example is probability of disease. So Department of Public Health is giving a free medical test for a certain disease. If the person has the disease, the test will be indicate disease 90% of the time. If the person does not have the disease, the test will indicate disease 10% of the time. The overall probability that a person has the disease is 1 in 10,000. If you decide to take the test and it indicates that you have disease, what is the probability that you have the disease? Okay, so let's solve this. Let event A equal you have the disease. Let event B equal the test is positive. And so this probability, the probability that you have the disease given that the test is positive, we're going to use Bayes' theorem. So the probability B given A times probability A, and then this piece of course is the same because it's one of in that sum. Then it's the probability B given A complement times the probability A complement. So let's just plug in the numbers. The probability that the test is positive given you have the disease is 90%. The probability that you have the disease is 1 in 10,000. And then that is just copied to this first piece. The probability you have disease, probably the test is positive given you have the disease is 90%. Probability you have the disease is 1 in 10,000. The probability that the test is positive given that you don't have the disease is 10%. The probability that you don't have the disease is 9,999 over 10,000, and this equals 1 in 1,000. So the probability that you have the disease given that the test is positive is 1 in 1,000. The next example, I'm going to call it coins in a box. A box contains 5 coins. Each coin has a different probability of a head. Let Pi denote the probability of a head when the ith coin is tossed. I equals 1 to 5. Assume P1 is 0, P2 is 1/4, P3 is 1/2, P4 is 3/4, P4 that should be P5, is 1. A coin is selected at random and tossed. Assume that a head was observed. What is the probability that the ith coin was selected? I equals 1 to 5. So let's let AI equal coin I was selected. Let's let B equal a head was observed. So let's let I equals 1. And we want to find the probability that the first coin was selected given that we observed a B. And we already know this is 0 because the probability of observing a head with coin 1 is 0. But let's go through the math because I think it's going to help. So the probability, let's use Bayes' theorem. The probability of randomly selecting coin 1 is 1/5. The probability that we observe a head given that we picked coin 1 is 0. And then these are the same numbers. I'll just put it 1/5 and 0. Now here, the probability that we do not select coin 1 is 4/5. The probability that we observe a head given that we did not pick coin 1, and that's this probability. So the probability of each of the 4 coins has an equal probability of being picked, so that's 1/4. And then coin 2 has a 1/4 probability of a head. Coin 3 has a 1/2. Coin 4 has a 3/4. Coin 5 has a 1. You do the math at 0. So let I equal 2. So the probability that we selected coin 2 given that we observed a head. Let's use Bayes' theorem. So probability that we select coin 2 is 1/5. Probability we observe a head given that we've selected coin 2 is 1/4. This in the denominator, the first term is the same as the numerator, 1/5 and 1/4. Now the probability that we did not pick coin 2 is 4/5. Then the probability of we observed a head given that we didn't pick coin 2 is this. So each coin has, each of the 4 remaining coins, each has a probability of 1/4 of being chosen. Then coin 1 has 0 probability of a head. Coin 3, right, not coin 2, coin 3 has a 1/2 probability of a head. Coin 4 has a 3/4. Coin 5 has a 1 probably 1 of being observing a head. So the overall probability is 1/10. Now, I'm going to go a little quicker over the next 3. The probability I is equal to 3. So we want to know the probability that we selected coin 3 given that we observed a head. We put in the math here. So, and then we get 2/10 when I is 4, and that the probability we selected coin 4 given that we observed a head is 3/10. Again using Bayes' theorem. Coin 5, the probability is 4/10 that we selected coin 5 given that we observed a head. Now let's do a quick simulation using R. So we're gonna have 5 coins, 1 through 5. We're going to store it in a variable called coins. We're going to do 500,000 replications. Now we're going to sample the coins. So that means the coins 1 through 5, we're going to sample it 500,000 times with replacement. So this variable, which coin, is going to be a vector of length 500,000, and it's going to be 1s, 2s, 3s, 4s, and 5s randomly, because that's what this sample does. And so that's going to tell us which coin we picked randomly. Now, once we pick the coin, we have to flip it. So this sapply, we're going to do this function 500,000 times. And the function is this. We're going to randomly pick a 0 or 1 based on the probability of a head. So we want a sample size of 1. Remember, we're going to do this for each coin. The size is 1, so that means we're only going to pick 0s and 1s. And we're going to pick a 1 with this probability, which coin minus 1 divided by 4. So if, and this is how you access a component of that vector. But if the coin is 1, we subtract 1, that's 0. 0 over 4 is 0, so the probability of a head on coin 1 is 0. If this is coin 2, we subtract 1, which is 1. So 2 minus 1 is 1. Divided by 4 is 1/4. So if we pick coin 2, then we're flipping the head with 1/4 probability. And if it's coin 3, then it's 2/4. Coin 4 is 3/4. Coin 5 is 4/4, which is 1. So it's the same probabilities that in the example. So flip is a vector of length 500,000, and it's going to be zeros and ones. And so it's going to be, and it's going to correspond to the coin that we picked in which coin. And if it's a 1 means we flipped a head. If it's a 0, we flipped a tail. So now the problem says, given that we flipped a head, so we need to isolate the coins where we flipped a head. So we're going to condition on flip equals 1. And we only want those coins. We're going to table them, see which coins we picked. And then, of course, we're going to divide by how many coins we flipped a head with. And let's table them. So coin 2, we observed it roughly 1/10 of the time. Coin 3 is 2/10. Coin 4 is roughly 3/10. Coin 5 is roughly 4/10. Notice coin 1 is 0, right? And it can't be because the probability of observing a head with coin 1 is 0. But there's lots of coin 1s in this which coin, but since we conditioned on a head, it's 0. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.